after 1 month. So we continued. So we finished 7.1 and 7.2. We finished 7.2 after we came back. Uh,
Oh, good.
so we just started 7.3 like a week ago.
Okay.
So yeah,
So
yeah,
actually, your topic 7 is a huge topic. It consists of three major distributions, you can say, as you told me that you have started 7.1. 7.1 is your discrete energy and radioactivity, right? So
yeah,
that related to, do you see my screen?
yeah. I can see it.
Yeah. So that is your discrete energy and radioactivity. I will explain these all one by one, that what do we go through in these topics, and then we will go back to 7.1, then 7.2, and then 7.3. And then the
Okay.
next one is your nuclear reactions. Okay.
Yeah,
Nuclear reaction. Actually, uh, if I classify this all, then I have to go in another sequence. So third topic is your the structure of matter. Okay. Structure of matter.
matter.
Right. Now, actually, what do we do? The discrete energy level is based on, or this is called atomic structure or study of atom. Okay. Atomic structure. Then we will talk about the mm, emission and absorption spectrums over there. Actually, that is also the property of the atom.
Yeah,
Then we have to talk about the radioactivities. Then we have to talk about half lives and all that stuff. This is a big topic. Then after that, we have to talk about nuclear reactions. In nuclear reactions, what we have to say, or what we have to go through, that how the nuclear process takes place, what type of nuclear reactions do we have in our nuclear physics. And then on the basis of that, we have to discuss about the structure of atom, sorry, structure of matter, not only the structure of atom. Okay. So this is basically the classification, we can say. So uh, I had all that stuff in my slides. I used to teach from that. So let's start from that, and I will explain you all of that topic one by one, inshallah. So the first thing what we are going to discuss in that, the main domain of the topic is atomic, nuclear, and particle physics. We call that topic this way. But in
yeah,
that one, as I told you, that the first one is your discrete energy and radioactivity. Okay. So what do you think
yeah.
when we talk about that, what an atom is? What do you think? What's your idea?
An atom is what? Uh, atom is the building blocks of matter.
Building block of the substance or matter.
Yeah,
So there were a lot of theories about atom and atomic structure, and all of that was basically explained on the basis of their own perception. It started
yeah,
from the Greeks. They started. Uh, they thought that they were philosophers, and they thought that yes, every material has a building block. As in biology, we have a building block like cell, but in matter or material science, the building block is basically atom. So I can classify that in living things, the building block is a cell which consists of a lot of atoms, but we can call it a cell. And in non-living things, the building block is your atom.
yeah,
Got it? Okay. Now, if we consider the nature of science, that how did we reach? Actually, Abdullah, whatever do we study, this all is revealed in our universe, and now we are getting that knowledge bit by bit by bit, from different observations. Some observations are reaching to us intentionally, and some observations are those which are reaching to us unintentionally. For example, this radioactivity was that field of science was revealed to us accidentally. We did not know that with this type of physics is existing, right? So there
yeah,
were two. This credit goes to Madam. Curie, right? She was then finally um, a victim of leukemia, because at that time we were not aware of the hazards and threats of these radioactivities. We were treating the radioactive sources as usual. They were just considered the rocks. So that was a point where we basically revealed this all, and we came to know that, oh, there are some sort of radiations or this type of things that exist in our daily life. So radioactivity was accidentally discovered, right? When Becquerel developed a photographic film that had accidentally been exposed to the radiation from. Actually, you know what happened? They got some rocks, beautiful rocks from some sort of uh, um, place wherever they were, and they collected those all rocks pieces in a jar, and they covered it just like we do in our daily life, in our home. And then finally they observed that, oh, it produced traces on that photographic paper, or that paper from which they were being those stones were being covered. So after that, this field has been evolved. So yeah, that was although that was an accident, but we had to study that. That's why. So don't think that they made this they created this problem for the student. No, actually they helped the universe a lot, but it depends upon us that how do we use that knowledge, or how do we proceed that knowledge to the others, right? So this is the first slide. It is basically related to those rocks and investigation of that, and how did all happen. Then in the next slide I have put all the data related to your understanding, that what you have to now in this topic, the discrete energy levels and discrete energy and energy levels. We should know that. I will explain to what are those. Then transition between energy levels, we have to go through this topic as well. This is the 7.1 subdivision. Then radioactive decays. Then I have to tell you about fundamental forces which are being used to keep the nucleons together. It's an amazing fact that all the nucleons which are which consist of like charges, and when we keep them together, it's huge repulsion in between those. And when we consider that, yes, in spite of that all repulsion, they are coexisting. It means they have very strong forces, force of attraction, or you can say strong nuclear force existing in between them. So after that, we have to talk about what are the radioactive radiations, nuclear radiations. Then they are considered as alpha particles, beta particles, gamma rays. Then we have to talk about half life in this topic. Then we have to consider absorption characteristics of the decay particles, and then isotopes, and then background radiations. These all are the subtopics which are basically discussed in our topic number one, discrete energy and radioactivity topic. Now is it clear to you?
Yeah.
Yeah. So right after that, actually I have divided these all topics into slides. So in discrete energy level, what are the applications area and what skills do you need in your IBs? So we have to now that how uh, this this these absorption and emission spectrum, they are related with the gases, and how do we now, by using the knowledge of emission and absorption spectrum, that what type of gas do we have. In further slides I would explain that on the basis of the spectrum color. I think because you have gone through the topic, you should have that awareness that with the help of color spectrum, or with the help of photons emitted from different gases, you know, we classify that, oh, this is hydrogen, this is helium, this is lithium, and all that stuff. Do you know that?
Yeah. Yeah.
Okay,
We did the
so
experiment
we
in
have
class.
to, yes, we have to discuss that all in this topic. Then in the next one, solving the problems involving the atomic spectra. like here we will discuss about that what type of transitions do we have, like in hot gases, basically the photons are absorbed in such a way that the electrons are descending from higher energy level to lower energy level, and similarly uh, they move from lower energy level to higher energy level. We have to calculate, we have to perform those calculations. I will go through that all. Then in next point, what we have to do, we have to calculate the photon, and I mean the wavelengths of the photons emitted. If you are aware of the data booklet or the formula sheet you have been given, in that we are given with an equation that E is equals to hf and E is equals to hc by lambda. So we will perform all the calculations based on that equation or that relation. Then we will have to complete the decay equations on the basis of these all decays, alpha decay, beta decay, and gamma decay. And then finally we have to talk about what are the half lives and half life stability curves, and then uh, those half life experimental simulation. We can go through that because that is related to your practical aspect. So half life can be determined from the decay curve. We have to go through that as well, right? So what is given to you in your data book, I have put all of that over here. The data book references are there. So as I told you earlier, that you would be given with E is equals to hf. This is the energy of photon from this equation is very famous from quantum mechanics. Max Planck has given this equation when he was having um, the studies of black body radiations and all that stuff. He gave that E is equals to, sorry, E is the energy of the quanta or the packet of light that consists of some sort of waves inside, and those waves are of wavelength lambda, right, or frequency f. You can say both the variables are correlated. And then he stated
Yeah.
that the energy possessed by each quanta is directly proportional to frequency of the photon inside it, right? That's why we write that E equals to hf, because h is the Planck's constant, and then we will use that equation. And then further, when we move on, we know that V is equals to f lambda, and f is equals to V by lambda, or because these all are the electromagnetic radiations, so I can say it is C by lambda. So I can write that E is equals to hc by lambda. From here, if I am interested in calculation of wavelength related to the emission and absorption factor, then I can say that lambda is equals to hc divided by E. So this all would be explained in detail, and it would be used because these equations have to be recalled. Uh, they are just to use. That's why they both are given to you in your booklet reference, right? Is it clear to you?
Yes, sir.
Okay. So meanwhile, Abdullah, if you want to ask any question, you are free to ask. It's a a class which
Yeah.
is not one-way traffic. It is two-way
Yeah.
traffic. You are
Okay.
allowed to
Yeah.
ask any question in between. Okay.
Yeah. Yeah.
So this is the
Sir.
slide. Yes.
Is it okay if we speed up a little bit because it's I feel like the class is a little slow. Like, sorry, but like it's a little slow because I want it to be more of a revision class rather than a learning class.
Yes, yes,
Is that
yes.
right?
I'm just pacing up. Actually, I thought that if we will go through the basics, then it would be fine. But let's go forward quickly.
Yeah.
Directly come to the point where we have to talk about the questions, right? So
Yeah.
this was basically your first atomic model. It was a renowned atomic model by Rutherford and his two co-workers or students. This is called your Giger and margin scattering experiment somehow. Then it is also named as Rutherford atomic model. They send or they basically bombarded alpha particles, and then by the alpha particles they observed that those alpha particles were bombarded on the gold foil, right? and when they were bombarded on the gold file, here are some sort of observations for you, that most of the alpha particles were passed through this. These traces show that most of the alpha particle passed through, few were basically bounced at larger angles, and very few were bounced at these angles, some were deflected. So these were the results, and on the basis of these three observations, we have rejected all the previous models of the atom, which were basically explained by different scientists of the time. So this is the first scientific model of our atom, and in that atom, this they have stated that yes, most of the alpha particle pass through. Why? Because atom was empty. Okay, these inference are asked to you in your exam, that why most of the alpha particle pass through. So because atom was considered as an empty space, or most of the space of the atom is empty, then why some of the particles were deflected? Because atom was having a positive entity in between, which was considered as the nucleus. And why very few were bounced back? Because this nucleus was very small in size. So whatever number of nuclei were in line with that, they were all bounced back, right? So this was one thing we have to consider. Then this is what this was the second aspect of our this topic of discrete energy levels and radioactivity. Actually, these all are the gas gases are fingerprints of gases to somehow. In next slide I will tell you that how do we treat them at the lower level, or you can say in the deep level. So there are some gas ionization in taking place inside the gases, and that those gases basically perform what? They produces glow. These all are the photons of different wavelengths. As I told you, that E is equals to hc by lambda is not equation only. It describes a lot of concepts, that the wavelength of the light is basically from 400 to 700 nanometer. And if we are going to consider that all of those seven colors are having different wavelengths, so depending upon that, whatever the energy or the voltages we will provide, we will have the wavelength or the color of the light accordingly, right? So these all colors are related to the different gases. So this is what this is usually the main concept of your discrete energy level. There are two types of spectrums. One is your line spectrum, okay,
Yeah.
absorption line spectrum, and the second one is your emission line spectrum. Okay, there are two types of line
Yeah.
spectrum. They are absorption and emission line spectrum. Actually, absorption line spectrum and emission line spectrum, they have a full concept behind it. When I say emission line spectrum, it means I get some sort of colored light or colored spectrum on the black dark or a dark background. And when I say that absorption spectrum, it means from a colored light, some waves have been absorbed, some colors have been disappeared, right? So what do we do when we have a sort of spectroscope is a device which is being used to study the spectral lines or spectrum. Then the colored lines appearing on the dark background is named as your emission line spectrum. And this was the word I had stated, that this is called the fingerprint of your element. Every element, every gas, they produce their own emission spectrum. And why do we have that? For example, they release the radiations due to distance of electrons from higher energy level to the lower energy level. And when the electrons are de-excited from higher energy level to the lower energy level, they produce a specific amount of wavelength, and that wavelength appears over here. Okay, so
Yeah.
this wavelength is, yes, do you have any question?
No, no, no.
Okay, then this is a comparison of continuous spectrum, absorption spectrum, and emission spectrum. It's very interesting fact that if we have a sunlight light source which consists of all seven colors, then from spectrometer, if we get its spectrum, this all would be continuous. No light has been disappeared. But if we have a cold gas is basically a gas in which, or at which we throw the light, and that light is being absorbed, and its electrons are excited from lower energy level to the higher energy level, and due to that, those photons which have been absorbed during this transition, they are disappeared from the line. Check this one out. Here, this was the photon which was disappeared. I mean, a green color photon has been disappeared. Here, an orange color photon has been disappeared. So, those photons which have been disappeared from here is a blue color photon. So, let's say there are three photons, mainly we are having three photons disappeared. Then that gas is now called as hot gas. Okay. So, if that gas is now again studied under the spectroscope, then actually we get all the photons back. It means the photons which are being absorbed by the electrons for excitation, during the excitation, the photon those electrons give us the same amount of energy back. That's why we have the emission line spectrum. So emission line spectrum is colored lines on or black background, and absorption spectrum is the black lines on colored background. Now is this difference clear
Okay.
to you?
Yeah.
Okay. Now here,
Sir.
yes.
So when you say that electrons are excited, are they excited by the heat or the electrical energy?
Okay, let me give you a free page over here for the discussion. Here would be yes. Yes. You know what happens if you have a gas? For example, I have an atom of the gas over here, and that atom of the gas is having uh, electrons in different energy levels. So suppose here is its shell number one atom. Sorry, shell number one electron. This is the shell number two electron. This is shell number three electron. So when you are going to incident the light, right? Let's say this is a blue light. I'm going to incident blue light, then red light,
Yeah.
and suppose green light. Okay, let's say there are three light waves what I'm going to incident on this atom. So if an electron is absorbing blue light, at the output I would have only two, green and red. So if I say that I observed that all on the dark background, then I will have just this blue. Instead of blue I would have a black line. Okay, I will have a black line over here. Red and green would be there. Let's say this is your green portion, this all would be your red portion, right? And this would be disappeared. In between this black would be disappeared. Now your question was that whether we are going to heat it up, we are going to incident photons on that, or what do we do, right? This was your
Yeah.
question, na? Yes. So did
Yeah.
you ever see the glow of iron when
Like
we heat up the
orange,
iron? Yes.
orange.
When we heat up iron, initially it does not give any color. So from there, the radiations are emitted. It does not mean that no radiations are emitted. The IRs are emitted from there. Okay, they are radiating IR. It means those all atoms of the iron which are getting energy from heat. Okay, heat can be provided it in any form, in the form of radiation or by any mean. Those atoms are getting excited from lower energy level E1 to E2. This was concept of Neil Bohr. And then when they are coming back, when they are being de-excited, they give you sort of photons. So when you are going to heat them up in such a way that they are able to produce red light photons. You know, red light photons are more energetic than IRs, because GXULIMR, in this range, this is gamma ray photon, gamma sorry, this is the electromagnetic spectrum. So IR is over here. Its energy is less than, according to E is equals to h c by lambda. Smaller the, sorry, larger the lambda, smaller the energy. So IR has larger lambda wavelength than that of light. That's why the energy of the photon is less. So if the electrons are excited from lower energy to higher energy orbit in such a way that during de-excitation they are able to produce less energetic photon than that of your red one, so you will not be able to see the glow. Okay, but as you heat it up more, you see the glow, and that glow gets, it converts from red to bluish color. Did you ever notice that?
No, no.
When you heat it up more, it it converts to bluish, mean to somehow purple color,
Oh yeah, yeah,
right? Bluish means that's not complete blue, but it's bluish, right? So it means that in light, if you divide the light into seven colors, if we I believe that you are aware of this: V, I, B, G, Y, O, and R. So red has the least energy, red photons, right? And violet has the most or highest energy. So that is over here in this portion. It means you are heating it up, those electrons are absorbing more and more energy, and they are reaching
yeah.
from lower energy orbit to higher and higher and higher. And when they are de-exciting back, they provides you the energy, and that energy would be of high frequency. So you can excite the electrons from any mean. There are three main excitations. One is your electric, second is your photo mean light, and third is your thermionic, right? That is from heat. Is it
Okay,
clear to you?
okay. So does the time it takes for it to get excited depend on the wavelength as well, right?
No, not the time actually. The photon which is emitted, let's say, let's have a detailed discussion about that. I like to have its explanation. If you have any query, when I will
Yeah.
explain it, uh, you can ask freely. For example, this is your shell
Mm.
number one, and its here energy level is one. Do you know the energy level diagram?
That one
Hmm?
line diagram, the
Line diagram,
forgot the
yes.
name.
So it is minus 13.6 electron volt level, which is called your ground state. Okay, it is your
Yeah.
ground state, right? And if the electrons are in the ground state, that is the first shell. So energy in any shell or any level, that can be calculated by E1 divided by 2 power 2 power n, n power, yes, n power 2, right? N power 2, not 2 power n, sorry, n square. So n is the number of shells. What is n? N is the number of shells.
The
So
number
at the
shells.
ground level, the energy level of the first or ground energy, it is minus 13.6 electron volt. So if I want to transfer an electron from lower, I mean first energy level to the second energy level, what energy do I need? 13.6 divided by 2 power 2 mean 1 by 4. So do you have a calculator?
Yeah.
Okay, just do it please. 13.6 divided by 4, will it be 3.5?
Yep.
Is it?
3.4.
Okay,
Yeah.
3, yeah, 3.4. So the second energy level is minus 3.4 electron volt. Now what would be the third energy level? Minus 13.6 divided by 9, it would be almost 1.5 to somehow. Is it?
Oh, okay. Yeah.
Got it?
Yeah. Yeah.
Then
Yeah.
fourth energy level is minus 13.6 divided by 4 power 2 means 16. So that would be equals to 0.85 or whatever. Calculations, you have to make calculations, right?
Yeah. Yeah. Yeah.
0.85.
85.
Okay, now in this way, what I say, that when I'm going to give energy to the electron, let me add few more pages over here, 2 3 pages for the discussion. And here, now, if I draw this all in specific graph or grid, I can say that yes, the energy levels, they can be, sorry, they can be done in this way. This is your, if it is, if I divide this all, just a graph, just like a graph, then if it is, uh, if this one is 0, then it can be 1 2 3 4 5, and let's say it is 6. Okay, I will delete this one, because when I will make it 6, I have to provide it a little bit more. Let's say this is 7. Okay, this is, let's say, your 7. Okay, so this is 0 1 2 3 4 5 6 and 7. Now my question, I have a question with you, that is, I'm going back from 0, so should I give, or should I provide negative signs to that?
No. So are
Yes.
you going back from zero or like towards zero or
Yeah,
away from zero?
I'm going down from 0. You know, when electron is an infinite energy level, this is your infinite energy level. Here n is equals to 0. Sorry, n is equals to infinite. So at that, your energy would be 0. No energy is required to keep the electrons orbiting over here, because the electron is not orbiting, it is an infinite energy level. So as it moves down, its energy levels are decreasing down and down and down. It has to lose the energy, right? Are you getting this thing?
Right.
Right. For example,
Yep.
the electron was at shell number 1, as I told you. Let's say this is your n is equals to 1, this is your n is equals to 2, this is your n is equals to 3, this is your n is equals to 4, and this is, let's say, n is equals to 5. So in n is equals to 1, when the electron would reach to the first energy level, exciting, sorry, de-exciting from infinity to this point, it has to lose, it has to lose minus 13.6 electron volt. So here, let's say this was, each energy level is representing 2. So it was, the first one is, suppose, minus 2 electron volt. Oh, sorry, I have put minus 1 2 3, minus 2 electron volt, then minus 4, minus 6, minus 8, minus 10, minus 12, and minus 14. So where would be this electron falling, or where would be this electron existing? 13.6. 13.6 is almost
Uh,
closer to
with,
this area, is it?
yeah. Yeah.
So this is your minus 13.6 electron volt level. It means this electron, which has lost this much energy from infinity, it was at infinite, this was a free electron. Infinity means it was a free electron. Now it has lost this much energy. Now it is reaching to this energy level. So it would radiate a photon of very high frequency. Are you getting it?
Yeah.
Okay. Now, when I say that, an electron is dropped from shell number in from infinite shell, or from infinity, from a free shell to shell number 2, then I told you that for shell number 2, the energy required over here, it is minus 3.4. It means it has lost minus 3.4 joules of the energy. So where is minus 3.4? It is your 4 and minus 4, and here it would be minus 3. So can you see what is the difference between zeroth energy level, I mean ground state, and first energy level? So here is your minus 3.4 energy level. Then what would be the next? Next is your 1.5. So where is 1.5? 1.5 is after
Between zero
this.
and two.
So as you
Yeah.
move up, did you notice that why these lines are getting closer and closer? Did you notice
Because
in any of the question
yeah.
they appear like this, na?
Yeah.
Exactly. So the motion of the electron from are in between these lines is called transition. Okay. So if you are going to heat up or energize or excite an electron, so what would happen? You are going to provide energy back to that electron. For example, if I have an electron in the ground state and I'm going to provide an energy to that electron, and if I'm coming back to your question, actually I had your question in my mind and I'm going to address that. If that electron is not able to absorb, or if this electron is not hit by a photon which is having the energy level equal to the difference of E2 and E1, that electron would not be able to move to the higher energy level. Are you getting this thing?
Yeah. Yeah.
So energy difference should be equals to minus 3.4 minus minus 13.6 electron volt. It must be like this. And now please calculate that. What will you get? Delta E.
10.2.
10.2 electron volt. Now come to the concept. If you are providing 10.2 electron volt, which is basically equal to 10.2 into 10 power, sorry, into 1.6 exponent minus 19, then it would be converted to joule. So if you are going to provide this much energy to an electron in the ground state, so will you please calculate that for me?
1.6 times 10 to the power minus 18.
Yes, this much energy is being now it depends upon you whether you are going to provide this energy by heat, by light, by electricity, or by kinetic energy of any other particle, like any other electron. You are going to bombard this shell electron with any other outer electron. If you will be able to provide this much amount of energy, this electron would jump from shell number 1 to shell number 2, mean higher energy level to the lower energy level to the higher energy level. Now is it clear?
Yeah.
Okay.
Yeah, that's.
Now, you know what will happen? Yes. Do you have a question? Is it clear to you?
Yes, sir.
Okay. Now, what would be appearing uh, on the spectroscope? Actually, you had bombarded a lot of photons on this atom, but only one photon have been disappeared, whose energy is equals to this. And if I want to calculate the wavelength of that photon, that which wavelength, which photon would be disappeared, so can I calculate that? Lambda is equals to hc by e. That's why that equation is given to you in your data booklet. H is your 6.63 into 10 to the power minus 34. What is the speed of light?
3 3.0 times 10 to the power of 8
Yes. And the energy is 1.6, you told me, minus 28. Is it?
minus 18.
Minus 18, sorry. Minus 18. Now, please calculate that for me. That what type of wavelength will you have?
1.2 times 10 to the power of minus 7.
Minus 7. So I can say it is almost 1 20 nanometer wavelength. Can I say that thing?
Yeah.
Good, very good. So, what is the wavelength of the light spectrum? 400 to 700 nanometer. It means this photon which have been absorbed or which was required, it is not from the light spectrum. Light will not be able to excite it. This is how much? This is from ultraviolet or any X-ray photon,
All right.
because its wavelength is less than that one, 120. So 120 usually
All right.
ultraviolet होता है. Are you getting this thing?
Okay. Yeah.
Right? So this is what, that how do we decide that which photon would be disappeared. Now, just a one question from you. Now I want to I've bombarded some light, and due to that light, an electron has been excited from minus 3.4 electron volt to minus 1.5 electron volt. This is my question. Okay,
Yeah.
are you getting it?
Okay. Yeah.
Okay, okay. Calculate the wavelength of photon disappeared or photon absorbed.
Okay. Sure.
So, what's
Yeah.
your plan to do that? You can tell me the plan. I would write it on the screen. You have to tell me, right? So, what's your plan? How to handle this type of questions? I have given you two lines, that an electron was at the energy level of minus 3.4 electron volt, and we bombarded that electron with a beam of light, and that electron has been
Hello.
excited to minus 1.5 electron volt. Now, my question is, which photon, or what is the wavelength of the photon which have been absorbed? Do you get my question?
Uh. Yeah. Sir, can you hear me?
Yes, yes.
Yeah. Okay. Uh. Okay. Oh, sorry. I got kicked out. I think my Opera browser crashed for like a few seconds, so I was kicked
Yeah,
out.
for
Can
few
you repeat
seconds you
the
were
question
disappeared.
again? Yeah. Can you repeat the
Yeah,
question again, sir?
yeah. My question is, I have bombarded a beam of photons, right, on this atom. This is a beam of photon. I'm going to explain it back to you. This is a beam of photon. There was an electron, and that electron was at energy level minus 3.4 electron volt. Due to this bombardment of the photons, that electron has been excited from minus 3.4 electron volt to 1.5 electron volt level, energy level. Okay.
Yeah.
Is it clear to you?
Yes, sir.
Now, my question is, calculate the wavelength of the photon which has been absorbed for this transition. And if I ask you what is the direction of transition, then you can say this is that. Okay, this is from my side. This one mark is awarded to you from my side. Yes. So, how will you
Okay.
calculate this wavelength?
Uh. So first of all, find the difference delta E.
Okay, delta
Uh.
E,
Which is which is delta E, which is minus 1.5 minus negative 3.4. Then you're gonna get 1.9,
very good.
and then you times the delta E by 1.6 times 10 to the power of minus 19.
Well done. So, why do we do that?
That's to find the HF, the free,
Yeah,
the,
we
so the
we
energy.
convert from electron volt to joules. Got it?
Yeah.
Okay.
Yeah.
Or this is the multiplication. By this multiplication, we reach to the joule. Now, what do we do?
So then now we use the formula of H HF
Okay.
divided HC, sorry, HC divided by, what's it, L? HC
Okay.
divided by
I mean, what is convenient for you? Are you convenient by using E is equals to HF?
HF, yeah.
Okay,
Oh no.
so here delta E is delta E, H and F is C by lambda. That's it. Just go for your own convenience. No need to cram it. No need to ratify that. You put the variables. Now make lambda as a subject. Then HC divided by delta E. Now,
Okay.
yes, very good. Carry on.
6.63 times 6.63 times 10 to the power of minus 34
Well done.
times 3 times 10 to the power of 8 divided by what's it, the previous year delta E value, which is
Yes,
3 point,
1.9 times 1.6
yeah,
exponent minus 19. Very good.
yeah, and then you're gonna get 6.5 times 10 to the power of minus 7.
6.5 into 10 raised power minus 7.
7.
It tells that it is 650 nanometer wavelength. So, if you remember that there is a sort of wavelength spectrum of your colored light. Oh, yeah, wavelength spectrum of your light. So, that is from 700 to 400 to 700. So I can say it is 400, then 450, then 500, then 550, then 600, then 650, and then 700, and finally it ends up at 750, and it starts from 350 almost. Now check this one out. From where it has been disappeared, this is V, I, B, G, Y, O, and R. So it has been disappeared from orange to red color. Is it?
Yeah,
So
orange
I
to
would
red.
have complete spectrum of light. Okay. All
Okay.
V, I, B, G, Y, O, and R. So in between these, this is the disappeared photon. Are you getting this thing?
Okay.
Yes. Now, I think you got your question that when we incident a photon of this much energy, then only the transition will take place. If the photon is not of that much energy, why all of the photons are not absorbed? Because they were not carrying that much energy. Is it?
Yeah.
So
Yeah.
the transition will take place due to only a suitable amount of energy which is being absorbed. So you told me that it was 1.9 electron volt energy have been absorbed during this transition. Now, in the next situation, this all is basically your absorption spectrum. This all detail was discussed due to your or regarding your absorption spectrum. The photon is absorbed, but we see the things due to emission spectrum. Emission
Yeah.
spectrum. Emission spectrum is basically the appearance of colored lines on black background. That's why I have selected black paper, black page. That photon which was absorbed in the previous transition, if if this electron is coming back to the excited state, sorry, to the ground state here in this way, so what will happen? It would release the same energy. It is changing the same energy. Now it is coming from E2 to E1. And how much energy change takes place? This much. It means due to this 1.9 electron volt energy change, the photon which would be released, it would be 650 nanometer. It will be 650 nanometer. Okay, are you getting it?
Yeah. Yes, sir.
Yes. मामा को बोलो कि उन्हें बोलें कि सारे घर पे नहीं है, वीकेंड पे दोस्त के घर गया हुआ है. Sorry for inconvenience.
No, no,
It's
it's okay,
weekend,
sir.
so I have to
Yeah.
make my kids engaged as well.
Yeah.
Okay, so is it clear to you
Yeah, yeah.
now? So you will get a line of at 650 nanometer range, which is almost your red and orange color photon. So this is what the game of all emission and absorption spectrum. I believe this thing that now you have no need to go through these slides one by one, right?
Yeah.
Because we have gone through a complete comprehension about this all, that what is happening inside. So will you be able to handle that? Only something would be
Yeah.
required for the memorization, that your wavelength from 0 to 200 nanometer, it's not actually 0 to 200 nanometer, but uh, these are some sort of wavelengths till 200 or 250 nanometer. We are having Lyman series. These are some series, and those series are actually when the photons are sorry, electrons are de-exciting from different energy levels. Let's say if this is the ground state, and first state, second, third, fourth, and so on, then if the electron is coming from infinite to first, right, then second to first, third to first, and so on, I will get a series of colored lines. Similarly, if an electron is coming from infinite to second, third to second, fourth to second, sorry, fourth to second, third to second, so I will get another range of wavelengths. Similarly, this all would be getting changed and changed and changed. So you are having all these series spectrums, that is called your Lyman series, Balmer series, and then Paschen series. These are actually the Paschen series in IR range. You are not able to see that. Then your Balmer series is in visible spectrum. This question is asked in few MCQs. I have seen that which series is or which is a visible spectrum. So that is the Balmer series, and the Lyman series is basically in your ultraviolet. Got it?
Got it. Yes.
Okay. Now, this was that type of discrete energy level, mean first seven energy levels. This would be the concept what I have given to you in detail. So you can go through these slides one by one, right? That from n1 to 7, these are the shell numbers, and then from shell number, we have to de-excite photon, or you can say we are going to incident a photon over here from at shell number 1 electron, and it is being excited from shell number 2 to shell number 3, right? So that electron, when it will de-excite, what will happen? Now it is during de-excitation, it is coming to the second, so it is just giving you the red color photon. So we just calculated this all. I believe this thing, that we have transited, we got the transition from second to third, and we were getting a 650 nanometer wavelength, and it was almost in the red color. So this was what I have explained to you, that these are basically the ready energy released from different conditions, that when electron is de-exciting from uh, to shell number 1, from different shells, I mean infinite shells, then it produces a sort of Lyman series. Then when these all drop to the second shell, second energy level, they produce Balmer series, which is visible, then Paschen, and then bracket, and then one. So these all are basically de-excitation levels. Is it clear to you?
Yes, sir.
Any question from this topic, this point? Sorry, from this slide?
No, sir. No, I understood it.
Okay, good. So this is again the same slide, but in a colored pattern, right? You know, this is the lower energy level. So from these two energy level transition, you are getting red. then yellow, then green, then blue, then violet, and to somehow maybe violet, more violet, deep violet, but probably maybe there was not color, that's why. Otherwise, because this is the highest energy level, so for the highest energy level we have to get violet instead of low energy level. In low energy level we are getting red ones. Okay, is it clear?
Yeah. Yes, sir.
Very good. So this was that what I told you. We discuss all these slides in a row. Okay, so we can heat the electron. These are the energy level there. Check this one out. Minus 13.6 electron volt, minus 3.5, 3.4, minus 5.1.51, and so on. So these are the line spectrum, as a line model, that the first two, it is very difficult to excite the electron from shell number 1 to shell number 2, because a lot of energy is required. 10.2 electron volt energy was required. But once you did it, now it is very easy to excite the electron from second to third, third to fourth, and so on. Right?
Yeah. Yeah,
Okay. So
definitely.
here, for your information, the electron transition energy is measured in the form of uh, electron volt, because that is very uh, small amount of energy. So we discussed that all. No need to go through back. Mean get into this again. If you have any question, then we can address that. So this is E is equal to HF pattern. We discussed this all. I have given you the value of H as well. This is called the Planck's constant, and E is the energy of the photon having frequency F. And this was the example. We have discussed that, I believe. This no need. Or if you have any question related to this, I can re-explain this to you.
No, I think I get it because this is also, I think, in chemistry. This is all.
Sorry. Yeah, it
Yeah,
is in
I read
chemistry.
through
Yes,
it.
exactly. It is also in your chemistry. So this all has been done. So here are some sort of the questions from your topics, that which one of the following provides the direct evidence of the existence of the discrete energy level of in an atom? Right, a continuous spectrum of the light emitted by the white hot metal, a line emission spectrum of the gas at the low pressure, because that low pressure means something that we have evacuated that tube, and the emission of gamma radiations, no. The ionization gas atom when bombarded with alpha particles, no. So it is just related to the pattern, so I have selected this option B for you. Okay, so these type of I told you that these type of questions are asked. Yes, exactly, this is that a sort of question that um, a spectrometer examine a glowing of a hydrogen shows that the presence of 434 nanometer blue emission line. What is the frequency of that? So you have to use this A is equals to sorry, V is equals to F lambda, or C is equals to V by F. Then you can get this one out. Then simply in stage 2 you are asked what is the energy in joule and electron volt. So we did that all. No worries about that. Then we calculated that what is the transition will take place. So the transition which is taking place for this, what is the what are the energy level associated with this photon. So we have selected that, okay, it is 2.86 electron volt. So 2.86 electron volt energy transition is basically between these two. uh, you will subtract these
Yeah.
all. So 3.4 minus 0.0544, you will get this energy level. Yes, do you have any question?
Oh no, yeah, I get it.
Okay, then this is basically again the solving problem from the atomic spectrum. Okay, explain why, what is mean by the term of absorption spectrum. So I think we have gone through this all. So if you have any query, I can address that. Otherwise I can shift to the next topic.
Sir, I think the time is up because it's been 1 hour for today's session. Uh,
You are now tired enough, huh?
yeah, and plus I have maths in like 45 minutes. So yeah, I have maths in 45 minutes. As for the timings, I feel like 1 hour is not enough for classes. Um, I'll first check the schedule. Are you free on Mondays? Okay.
um
Mondays.
Actually,
7
your
p.m.
time is
Brunei
a
time.
bit ahead, so I have to manage that. I mean, I will give you the time slot, timetable. Actually, I follow the timetable in this way. Let me show you, because uh, you are your screen is my screen is shared with you, so I can show you the timetable over here instead of sending you on that. Okay, okay. Yes, I have a lot of schedules in my Excel sheet, so hopefully, if I get it or if it would be open, then I can show you that. This is not what was that other one. I believe that 3 to 4 classes would be mandatory. Otherwise, you know, it would not
Because
be.
I, because the point is, I cannot have 3 to 4 because I don't have time for 3 to 4. Maybe like two classes is okay, but two classes for like, uh,
This is my timetable. It is really colorful and packed slots. So I start right from here, meaning during this time I had school classes as well, but I have to arrange anywhere. So that's why I have given you slot over here for today, because I was not having any plan to shuffle the students. So I can make a slot over here instead of Mahad, because Mahad is busy in these 2 days with some other activities. So here we can have 2 slots. This is
eh,
8 to 9 Pakistani time. Um, it would be
uh,
your, oh my god, it would be your
11,
11 to 12.
11.
Oh my god, it would it would be so late. So
I like to check first because I'm thinking about after because I also have my own schedule. Uh, I also have a very colorful schedule.
oh yes, yes, you can say. Why I said I showed you this one, because I want that you have to tell me
Yeah,
your convenient time as well, because the main thing is that now you would also be engaged like me,
yeah.
because you would have how many subjects you are taking? Maths, physics, and
Just that maths, physics, and chemistry. But chemistry is only like on Sundays for like an hour and a half. Um,
okay, and for maths.
maths is usually in the afternoon, like around 1 Brunei time, one to
Okay,
three, 1 to 3. But today the teacher is busy, so today is in the evening. Um,
okay, good.
Saturday and
So
Sunday, we could do Saturday, Sunday, um, 8 p.m. Brunei time, 8 p.m. Brunei time, but instead of 1 hour, I'm thinking about 1 hour 30. But I will get back
what
to you.
about
I'll
this
text
time?
you.
I mean, what about Saturday and Sunday Brunei time? Uh, what is 10 plus 3? 1 o'clock, 1
Oh
p.m.
no, that's maths tuition. I usually have maths tuition.
Okay,
Cause
so you
yeah,
would be over there anywhere at this
yeah.
area.
Anyway, yeah. I will let you know.
Yeah,
I'll
it's
just
fine.
first look at my schedule and I'll let you know.
Yeah, that's fine. Then we will be, inshallah. I will give you the timetable in the same way. I will give the slot to you, and then we will
Yeah.
try to follow the slots,
Yeah,
because
sure.
nowadays, honestly speaking, I talked to sir as well, Sir Dawood, right?
Yeah, yeah.
Your
That's
match
my
teacher
math.
is Sir Dawood, na?
Yeah. Yeah, yeah.
Yeah. So he requested me, just like that, you have to give one slot, no problem. Whatever your schedule is, but you have to create a slot.
Yeah,
So that's why.
I have to change because because my slots right now, not my slots, but like my schedule is like fitted to my final exam schedule, and because I want to get through the entire physics syllabus, we do like review session. Like I want to do 1 hour. I want to do 1 hour 30 minutes. 1 hour of like going over the topic, like just review, just like brushing over a topic,
Yes.
calculating, and then 30 minutes of just questions. That's what I wanted.
Yeah, that's fine. So we will divide the slots. Yeah, I can have another idea. For example, if we for one day we go through the entire topic, just overview, and for the next day or for the next session we use to do its topical questions. So how will be this working? Will
Oh,
it
that
be
would be
fine?
no, no, that would be blessed. Yeah. All
Yes,
right.
because Abdullah, what I want from you, that for example, I have gone through this topic. Do you have some sort of printed topicals,
Do you mean like the
or you use
like
from online?
notes?
No, no, no.
I have
I mean the topic questions for
topic
practice.
questions. I have saved my exams, but my friend hasn't. We still have to buy our account again. We have to refill it. But I will. But I
Okay,
have
okay.
questions from
So
there.
okay, good. So
And then
I mean, you
there's
have downloaded those.
not downloaded. I still have to get them.
Okay.
Because they're all online. But I will once
Oh
I
yeah,
do get
IB
them,
is
I'll let you
almost
know.
online. So I have few
Yeah,
websites from there we can download the stuff. But I have downloaded stuff. I will send to you. You can take print out of that,
yeah.
and then
Oh yeah.
it would be
I
quite
have
easy for you.
also yeah, I also have every single IB past paper from 1999 as well, so we don't have to worry about
Oh,
yeah.
1999, before your birth.
I have a lot of IB past papers, every single one of them. So
Oh,
yeah. Yes,
are they downloaded?
uh, I don't download them because I don't want to take too much space, but when I need them, I will download them.
Yes. So what will we do? You would or we will decide together that yes, you have to go through this past paper. Okay,
Okay. Yeah.
you will solve that, and when we will have a discussion session, you will tell me that yes, I have gone through this past paper and I have the problem in this area. So that past paper would be available to me. You will send me the link of those where these 9 till 99 to from where you are working basically, and then I will open the past paper over here instead of you send snapshots to me that I got problem in this big question and this question and this question. I will just open it up over here, and you have
Okay,
to
yeah,
tell me
sure.
that okay, I was having problem in this area, and we will be going through that. Will it be easy?
Yeah. Yeah.
Yes.
Okay, yeah. For the past papers, you actually have to download a different browser. It works on a different browser.
Yeah, we will follow up same one because we have to plan it. Listen, I have the plans like this. Let me show you one uh, plan over here. Maybe that I have shuffled anywhere. Okay. I would like to have a proper revision plan. I mean, I will make it like just like this one. Yeah, this is for A levels. This is not for your IB, but check this one out. So in this way, you will be bound to do a set of questions, right? Just like it is A level, so it would be P1, P2, P3, and so on. So I will prepare your topical practice as well, right? Said from which
Yes.
topic you have to go through which paper, structured questions are MCQs at which day. So you would be doing that according to the timetable. I believe that it would help you out. Otherwise, randomly, it would not help you out.
Yeah, understand. Yeah.
Did you get it? So this is plan from my side. Now it's up to you. You have to let me know about your schedule and your availability. Then we will decide inshallah together. Okay.
Right. Yeah, inshallah.
Okay.
Okay.
See you
Okay.
at
All right.
Allah Hafiz.
Allah Hafiz. Thank you,
Allah
sir.
Hafiz.
Assalamu alaikum.
Walaikum salam. Walaikum salam.